Hi guys, thanks for tuning in. In this video, I'm going to talk about using integrals to measure flow along. Now in this first example, I'm going to take a vector field y comma 2x, and I'm going to have it act on a curve e of t, which is really just an ellipse centered at the point -1, comma 1. Now our job here is to measure the net flow of the vector field along this curve. And if you remember the previous chapter, you can kind of think of this like the red curve is a set of underwater train tracks, and the train, as it goes counterclockwise around that track, is being hit by the swirling currents that the vector field is causing. And we kind of want to think about the net effect of that vector field on our train as it takes a full loop around that train track, around that curve. But honestly, that picture is pretty hard to interpret, so we can get a better picture of what's going on by just plotting the field vectors whose tails are on the curve. So here it is. We produce that plot just by plotting field of x of t, y of t, and making sure that we put those vectors with their tails at x of t, y of t on the curve. Now, I purposely picked this example so it's not super obvious if the net flow of the vector field along the curve is clockwise or counterclockwise. I wanted an example where there is a clear answer, but eyeballing the plot doesn't necessarily produce that answer. We want to try to get more precise. And so if we want to get a better picture of what's going on, remember that instead of plotting just field of x of t, y of t, we could look at the push of the field vectors in the direction of the tangent vectors. And so that's what we're going to look at on this slide. So we're going to do field.tangent over tangent.tangent times the tangent vectors. And there's the plot it produces. And again, you get a better idea of whether the net flow of the vector field along that curve is going to be clockwise or counterclockwise. But it's still not super clear cut. You can see we have like a bundle of vectors over here that are pointing in the counterclockwise direction. And then we have two kind of bundles of vectors that are pointing in the clockwise direction. And it's not super obvious if the net flow of the vector field along that curve is going to turn out to be clockwise or counterclockwise. And since we're not 100% positive, we want a more concrete method for performing these calculations. Really, if you look at the expression from the previous slide, the part that really measures with or against, whether the field vectors are with or against the tangent vectors, it's the numerator of that fraction, right? Field.tangent really is what's giving us our measure of whether the field vector is with the tangent vector at a particular point or if the field vector is against the tangent vector at a particular point. This is the thing that can vary between positive and negative. So in a sense, that's kind of the quantity we want to accumulate, because as we accumulate all of these little pushes with or against our tangent vectors, that'll give us an overall idea of the net effect that this vector field is having on our curve. So that's what we're going to integrate. We're going to take the integral from 0 to 2 pi of field.tangent dt, and that should give us a pretty good measure of whether the net flow of the vector field along that curve is going to be with our tangent vectors, a positive answer, or whether it's going to be against our tangent vectors, a negative answer. So we can crunch the numbers pretty easily here. We set up the integral of field.tangent, and you go ahead and you plug in field of x of t, y of t. That's just our vector field y comma 2x with x of t, y of t plugged in for each instance of x and y. That's what you see right here. It's simplified for you though. And then we also have x prime of t, y prime of t, and you could see pretty clearly here the derivative of cosine is negative sine, the derivative of 2 sine t is 2 cosine t, and then the center of that ellipse doesn't matter so much since the derivative of a constant is going to be 0 in both cases. So we're going to evaluate that dot product, and these problems very frequently give you a single integral that involves a lot of sines and cosines and powers of sines and cosines. So that's what we get here. You want to get comfortable integrating expressions like this by hand, because you are going to see these as the course progresses, lit sheets, quizzes, maybe at the end of the year if we get to take a final in person, you might have to produce some of these calculations without the aid of Mathematica. But for now, I'm going to leave this hard work for you guys, and I'm going to tell you that this integral works out to 2 pi. Now, we get a positive result here. You are never done with these problems when you get a numerical result. This is your penultimate step. So 2 pi is good. You did a great job getting that calculation, but you need to interpret. So this is a positive quantity. And then we write a complete sentence. The net flow of the vector field along the curve is in the direction of parameterization, which in this case turns out to be counterclockwise. So that interpretation step is going to be worth points every single time it comes up. So getting to the numerical answer, great. Now you need to interpret that numerical answer. The net flow of the vector field along the curve is, since it's positive, in the direction of parameterization, in the direction of the tangent vectors, which in this case gives us counterclockwise. All right, so up till now, we were kind of integrating because we picked up the idea last chapter that we're doing some sort of accumulating, right? We're accumulating the net effect of the vector field, of the field vectors on our curve, on our tangent vectors. And we already know that the tool in a calculus course that accumulates things is the integral. So we kind of knew we had to integrate in some way, shape, or form. And what are we accumulating? All of the little pushes with or against, right? All of the little pushes of those field vectors with or against our tangent vectors. And if we accumulate across along that entire closed loop for our closed curve, we know the net effect. And we're going to get an answer of clockwise or counterclockwise. But we could probably be a little bit more precise here. There's various ways of proving that that formula works. What I've found is pretty effective over the years is just kind of showing some correspondences between the kinds of integrals you guys were doing last year in your Calc BC course versus the type of path integral that we're going to be computing in this chapter. And I might post some other videos with some other perspectives that might help you. But for now, I think teaching through analogy is probably going to be pretty effective. So here's an expression from last year, the integral from a to b of f of x dx. And our integrand is a function of a single variable. The path that we're taking is we're following an interval a comma b along the x-axis. And we're integrating with respect to left-right movement, right? We're integrating dx. So we're moving along the x-axis, and our accumulation is happening along the x-axis there. And you could kind of think of this f of x dx as f of x times dx in the sense that if you remember doing that LRAM, MRAM, RRAM stuff, you had a rectangle of area, and the height of that rectangle was given by the function. And the base of that rectangle, we had delta x when we were setting up Riemann sums, but then in the limit as you progress from a Riemann sum over to an integral, then that delta x becomes a dx. And so we could think of this f of x times dx kind of like a base times a height, the area of a rectangle. All right, so now let's compare with what we're doing in our current chapter with path integrals. And this is the sort of notation that you might see in a more traditional multivariable calculus textbook. But don't get scared of this notation. It's the same thing I was showing you on the previous slide. The integral of field dot tangent is still hidden inside of this notation. In a lot of textbooks, you see field shortened to just f. Kind of the difference between when you're doing things on paper by hand versus when you're doing your calculations in Mathematica. In Mathematica, it doesn't take very long to type out field, and so it's kind of nice to type out field in your code so that you have a descriptive variable name and you know what it represents. When you're doing things by hand, writing takes longer, and so you just shorten it to capital F. Now, what do we have going on in this path integral here? Okay, so we have a two-component vector field, f of xy, that's our field. Now we have a curve in space, capital C, that has some parameterization, lowercase c. And the idea here is that we're going to integrate with respect to movement along our parameterization, kind of like a DC, right? Moving along some parameterization of some curve C. And instead of multiplying right here, we have our dot product, field dot tangent, f dot dc. So that's kind of the correspondence between last year's material and this year's material. So now let's take this expression and see what we can do with it. So you can see that everything is analogous here, right? Integrating, everything's color-coded, right? So you could see a function of a single variable from last year is a two-component vector field this year. Our interval along the x-axis from last year, now we're accumulating along a curve that's in space, that's parameterized. Last year we were integrating with respect to a change in x, a dx. Now we're moving along a parameterization dc, and last year we had f of x quote-unquote times dx. And in this chapter, we have capital F of x, our vector field, dot dc. But it's still kind of like a product there, right? It's a dot product. All right, so let's take that notation and let's start to break it apart. So first of all, kind of weird to think about integrating dc. That's not really very familiar. Integrating with respect to a change in arc length is not really a very intuitive idea. Integrating with respect to a change along a parameterization, not very intuitive. We kind of want to move along dt with respect to our parameter, right? With respect to a change in t. Well, we could use chain rule to break this apart, so we need a dc dt right here, and then we can change this to a dt integral. So you can see what happened. X got substituted with x of t, y we could replace with y of t, we're parameterizing here, and then if we make that change, then dc can become dc dt times dt. Well, dc dt looks like it's an unfamiliar format, but I mean, we've been using notation like this all year. That's c prime of t. So if you think of c of t as your parameterization, c prime of t is x prime of t, y prime of t. Oh, and there it is. That's our formula from this chapter. Our path integral along our curve x of t, y of t. It's the integral of field dot tangent dt. So here's the formula that we're going to be using to do most of our calculations in this chapter. Very useful formula. Now, in some textbooks, you'll hear this called a line integral. In other textbooks, you'll see it described as a path integral. I am not a huge fan of line integral notation or terminology. And the reason is it makes it sound like your x of t, y of t needs to be a straight line, which it most certainly does not. I like path integral better because I like the idea that we can take any path in two-dimensional space called C, and we can accumulate as we follow along that path. And it doesn't have to be a straight line. Certainly it's convenient when we integrate along a straight line, but that's in no way a guarantee in this course. So I kind of like path integral as my preferred terminology. All right, so you're going to see several different equivalent notations sprinkled in throughout the basics and tutorials and try-its in this chapter. So this is my favorite. And the reason that this is my favorite form for a path integral is, first of all, it's constructive, right? You can go into Mathematica and you can write code to perform this computation. The integral of field of x of t, y of t dot x prime of t, y prime of t dt. You could write code where you define your vector field of x, y. You define your parameterized curve x of t, y of t. And as long as you know your bounds, Mathematica can integrate this. So it is very good for performing computations. But I also think it's intuitive, right? What is this integral accumulating? It's accumulating a bunch of little pushes of our vector field with or against our tangent vectors. So is the net effect of this vector field on the curve that we are getting a push that is with the tangent vectors, or is the net effect that we're getting a push against our tangent vectors? I think that the integrand is intuitive, and I think that the actual setup for this integral is nice for evaluating code and getting an answer. Now that being said, there are some other notations that are somewhat useful or very useful. So remember that our vector field, if that's some m comma n, you could replace your vector field, your field of x of t, y of t with m of x of t, y of t, n of x of t, y of t. And then you can evaluate that dot product. And you get this format. The integral of m of x of t, y of t, x prime of t plus n of x of t, y of t, y prime of t dt. Now, this one's perfectly good notation as well. It also runs nicely through Mathematica. This is also constructive. The drawback is it's a lot more typing. Look how much longer this expression is. However, it does have a benefit. It might remind you of a formula that you've seen in a previous chapter, the Gauss-Green formula. So this box is kind of, I don't think I made it green on purpose when I first made this PowerPoint, but if I did, kudos to me, because it's in a green box, and it's this is half of the Gauss-Green formula. So this kind of previews something that we're going to see soon in this course, next chapter. Finally, there's one more notation that we can write, and that's a deparameterized version. The blue box at the top, the green box in the middle, the drawback that they both have is it takes a long time to write out those formulas. There's lots of x's and y's and t's and primes and m's and n's. It takes a really long time to type it out. If you deparameterize though, if you kind of do this chain rule thing in reverse, so you write your x prime of t as dx dt, and then we kind of quote unquote distribute the dt into each of these. You could kind of imagine the dx dt and the dt kind of canceling in a chain rule sense, and your dy dt and your dt canceling in the sense of a chain rule. And we can deparameterize this to the path integral along C of m of xy dx plus n of xy dy. And this notation is not great for doing computations, not great for calculations, but it's a really nice shorthand because it's pretty fast to type out this expression right here. It's just nice and condensed. It's compact. So we like it because it is compact, and also it doesn't depend on any single parameterization of your curve C, which is also beneficial. All right, so this slide is really just a summary of everything we've looked at so far. So we have three equivalent notations for a path integral: the integral of field dot tangent, the integral of m of x of t, y of t, x prime of t plus n of x of t, y of t, y prime of t dt, and then the integral of m dx plus n dy. You should be familiar with all three. You should be able to change back and forth between any of the three, and you should know which ones are good for computations and which ones are good for explanations. The basics and tutorials are going to flip-flop between these notations without any warning, and so you kind of have to just keep up with that. There is a little bit of new content on this slide, which is right here. If you are lucky enough to have a closed curve, you can write your path integral with a little loop on your integral symbol. And this symbol just indicates, it actually doesn't change anything about how the integral is computed. Sometimes there's some shortcuts for closed curves, but besides that, it doesn't really change how the integral gets computed. So this is not like a quote-unquote different kind of integral. This is the same as any other path integral, but this little loop is a visual reminder to the reader that you're performing a path integral along a closed curve. So this is an indication that C is closed. You know, something that, if it's not a circle or an ellipse, is, you know, kind of like a deformed circle or a deformed ellipse of some sort. If C is not closed, then we can't write that little loop because that doesn't make any sense. And you guys are going to perform both kinds of path integrals. I would highly encourage you to use this notation with the little circle for two reasons. One is it's a good reminder to yourself of what kind of curve you have, and there are special properties of closed curves that you want to keep track of. Also, the symbol just looks kind of cool, right? Remember when I first saw the symbol, I felt really smart writing down an integral symbol with this little loop because it looks cool. So that's my other selling point for describing a path integral along a closed curve in that way. And finally, guys, one thing I should mention is there is a common physics interpretation of flow along, and that is work. And so you're going to see that come up in various application problems. And if you take any more advanced physics courses, it's going to be very common for you to compute path integrals to compute work. All right, so let's put this all together here. So if we compute a path integral along a closed curve that happens to have a counterclockwise parameterization, and if we get a positive result, that means that the net flow of the vector field along that closed curve is in the direction of our tangent vectors, or because of the nature of our parameterization, counterclockwise. Likewise, if you get a negative result, clockwise, and it is always possible for your path integral to compute to 0. All right, so let's crunch some numbers here. So I've got the vector field 3y comma negative x squared, and I've got this ellipse. Now, one thing you're going to need to be comfortable with is parameterizing an ellipse without having to think very hard. So here's my vector field and my curve. You guys are going to have to parameterize ellipses like this from an xy equation. Now, this picture is not very helpful. Can't really tell what's going on here. I can improve my plot by plotting field of x of t, y of t. That's better. And I could see, could start to get an idea that I think that the net flow of the vector field along this closed curve is probably going to be in the clockwise direction, but I'm not going to make any guarantees till I actually crunch the numbers. And we could further improve this picture by looking at the component of the field vectors in the direction of the tangent vectors. And remember that one of the dot products that is used in computing these vectors is actually what we're going to accumulate. We're going to integrate field dot tangent to get our numerical result. And this picture, I am very confident that the net flow of the vector field along this closed curve is going to be in the clockwise direction. All right, so let's crunch some numbers. So there's my vector field, 3y comma negative x squared. There's my ellipse, 2 cosine t comma sine t plus 1 comma 0. And I want to compute the net flow of this vector field along this ellipse. Now, the first thing you want to check is that you have parameterized your curve, your x of t, y of t, in the counterclockwise direction. If you ever see a path integral, you want to assume that that path integral implies that you need counterclockwise parameterization. You want to assume that this path integral symbol, if you see this little loop here, that it is demanding a counterclockwise parameterization. There's some exceptions to this and some try-it problems where they have you explore what happens if you have a clockwise parameterization and how to fix your answers when you do that by accident. But for the most part, if you are coming up with your setup on your own from scratch, you want to assume that the parameterization for your curve, your x of t, y of t, should go in the counterclockwise direction. All right, moving on. So here is this notation for a path integral for flow along that is not very good for doing computations with, but it looks cool, neat looking formula. Let's switch it over to a formula that we can actually work with. So this is the one that looks like the Gauss-Green theorem here. And we have enough information to plug in everything we need. I can easily compute x prime of t and y prime of t from my x of t and my y of t. I can easily compute my m of x of t, y of t, and my n of x of t, y of t just by plugging in my x of t, y of t into my vector field. And when you expand it all out, you get this single integral that is in terms of lots of powers of sine and cosine. You guys will have to get comfortable with integrating expressions like this. And when you actually crunch the numbers, you get negative 10 pi, which confirms my earlier suspicions that the net flow of this vector field along this closed curve is going to be against the direction of the tangent vectors, or it's going to be clockwise. Remember that you are not done with these problems till you write a complete sentence summarizing your result. The net flow of the vector field along the curve is against the direction of parameterization, or against the tangent vectors, or clockwise. Anyway, guys, thanks for tuning in. In my next video, I'm going to talk about flow across.